So it is my pleasure to introduce Ziwen Zhu from the University of Utah, who will speak about equivariant K-stability under finite group action.
Okay, thank you very much for the invitation, and it's my great pleasure to speak at the SDAC seminar. Okay, so I'm going to talk about equivariant K-stability, and I will mostly focus on the case under finite group action. So before I start my talk, let me first of all mention the settings of my talk. So we will work over the field of complex numbers. And so when I talk about a Q-Fano variety, it's going to be a normal projective variety with, at worst, KLT singularities, and the anti-canonical divisor is ample. Okay, and so at the latter part of my talk, we will also work with log-Fano pairs. So this is going to be a pair with KLT singularities as well, and the anti-log canonical divisor is going to be ample. And usually we will denote by n the dimension of the variety X we are concerning. All right, so first of all, then let me mention some of the motivations of studying K-stability and equivariant K-stability. So first of all, there's this well-known theorem by Chen, Donaldson, and Sun, and Tian, where when people are considering the existence problem of a K-line symmetric on a Fano manifold, we have the famous theorem saying that this analytic condition is in fact characterized precisely by K-polystability, which is defined purely algebraically. Okay, so this is, I think, the starting point why people are interested in the question of K-stability. And of course, recently there's a rapid progress in the question about constructing K-moduli of Q-Fano varieties or log-Fano pairs, which also is an interesting question related to K-stability. Okay, and however, in general, if you're given a concrete example of a Fano manifold, it's in fact not easy to verify the K-stability conditions using the definition via test configurations, which I'll mention later in my talk. Okay, then people try to study also the notion of equivariant K-stability. And equivariant K-stability is defined via equivariant test configurations. And here for equivariant test configurations, these are test configurations with an additional assumption about the G action on the variety. So we will mention in more detail about the definition later. And one advantage about equivariant K-stability is that, so for a lot of examples, so for the Q-Fano varieties with large symmetry, sometimes it'll be easier to check equivariant K-stability. And a couple of examples we will look at later are, so the basic example is going to be the projective space, or more generally, homogeneous spaces. And we will also look at a more concrete example about Fano threefolds of degrees 22, which is studied by, this is a class of Fano threefolds studied by Chalsov and Shramov, and they computed the equivariant alpha invariance of these degree 22 Fano threefolds, admitting a group action of C star semi-product with Z mod 2. Okay, and these are a couple of examples where usually it's actually easier to verify equivariant K-stability. And the usefulness of verifying equivariant K-stability is the following conjecture. In fact, so for a Q-Fano variety, if we consider a reductive group action, then if we can verify that X is G equivariantly K semi-stable or respectively G equivariantly K polystable, then X itself is actually going to be K semi-stable or respectively K polystable. Okay, so therefore in applications for concrete examples, if we can verify equivariant K semi-stability or equivariant K polystability, then we can deduce the corresponding K semi-stability or K polystability of this variety. Okay, so then let me maybe survey through a couple of recent progress about this conjecture. So the first solution of the conjecture is the smooth case. So Data and Ziwen, they use analytic method to and they show that for Fano for Fano manifolds, they show that if X is equivariant, G equivariantly K semi-stable or G equivariantly K polystable, then the corresponding Fano manifold is K semi-stable or K polystable. And in fact, the method they're using is purely analytic, and they try to construct the K-Einstein metric using a more refined statements from the Chen, Donaldson, and Sun's paper. Okay, and the second solved case for the equivariant K-stability conjecture is by Li Xu for the K-semi-stability case, and then by Liwang Xu for the K-polystability case. But this is for all Q-Fano varieties, not just for the smooth case, but we're restricting to the case where we're just looking at torus actions on the variety. Okay, so this is the second case, and their proof is purely algebraic. And the third case is solved in my joint work with Yuchen. So this is for the finite group action case. And again, this is for any Q-Fano variety. And our method actually relies on a quite sophisticated analytic result, which is the solution to the uniform YTD conjecture by Li Tian Wang, which states that if Q-Fano variety is uniformly K-stable, then there exists a K-Einstein metric on this Q-Fano variety. Okay, so this is the third case. And recently, Ziwen fully solved this conjecture. Basically, he worked on the general case for Q-Fano varieties and for arbitrary group action, if we are just looking at K semi-stability case for the conjecture. And if the group is reductive, he also solved the K polystability case for the conjecture. Okay, so therefore the conjecture is fully understood for all cases. Okay, so in my talk today, I will mostly focus on the third case, which is the finite group action case. Okay, so next I'll probably start with, first of all, the definition of equivariant K-stability. So I will first talk about the definition for an equivariant test configuration. So before I move on, any questions? Okay, so first of all, let me recall the definition of a test configuration. So a test configuration of a Q-Fano variety X, it is going to be a degeneration of X over A1, which is GM equivariant, and outside the central fiber, it's GM equivariantly trivial. So outside the central fiber, it's GM equivariantly isomorphic to X cross C star. And and we have the fiber over 1 to be isomorphic to X, and we have the compactification over the 0 fiber. So it is going to be called a special test configuration if the fiber over 0 is also a Q-Fano variety. But in general, for a test configuration, we don't necessarily require the 0 fiber to be irreducible or reduced. Okay, so this is the definition of a test configuration. Now, if we assume we have a group action on X, the Q-Fano variety we start with, then there's a natural induced G action on X cross C star, which is the part outside the central fiber of the test configuration. So we can have this G action on X cross C star in the following way. So basically, for any fiber over T in X cross C star, we have that the G action is given. First of all, we move this fiber over T to the fiber over 1 using the GM action of this test configuration, which is the one parameter subgroup lambda T, I denote here. So I move this fiber back to the fiber over 1, and then I use the G action on the variety X for this fiber over 1, and then I move the fiber over 1 back to the fiber over T. So basically, we conjugate the G action with the one parameter subgroup to get induced G action on X cross C star. Okay, so therefore, for any test configuration, as long as we have a G action on the Q-Fano variety X, we start with, then we can have this induced G action on X cross C star. And this G action actually commutes with the GM action of this test configuration on X cross C star. All right, so then the additional assumption that we want to put on a G equivariant test configuration is that the G action we have on X cross C star, we want this G action to extend actually to the whole test configuration curly X. And again, we want this action to commute with the GM action also along the fiber over 0. Okay, so this is the additional assumption we have for for a test configuration to be also G equivariant. Okay, therefore, so we see just from the definition that G equivariant test configuration is actually a smaller class among all test configurations. Okay, so this is the definition for equivariant test configuration. And then I want to also recall the definition of the Futaki invariant of a test configuration. Okay, so for any test configuration, we can compactify equivariantly the test configuration to a degeneration over P1 by adding a fiber equivariantly over infinity. And then if we start with a normal test configuration, then the compactification is also normal, and then we can compute the Futaki invariant using the following intersection numbers. So okay, so this is the formula for the intersection number, which computes the generalized Futaki invariant of a test configuration. Okay, so this is going to be used in later computations of my talk. Okay, so then I also want to define, I also want to define the norm of a test configuration. So there are a couple of various definitions of norms, and all of them are equivalent to each other, meaning that in the sense of equivalent norms. And I think in Harold's talk a couple of weeks ago, he also mentioned a couple of definition of norms. Let me mention one of them, which is used in the valuative criterion, which I'll talk about later. So this is the non-Archimedean norm defined in a paper of Buxon, Hisamoto, and Johnson. So for the non-Archimedean norm of a test configuration, first of all, I look at the graph here. So for a test configuration, it's birational to the product X cross P1, where on X cross C star, we have the equivariant isomorphism. Okay, so we look at the resolution of the graph of this birational map. So we have the map Y, curly Y to X cross P1 with the morphism P, and then we have Y of the morphism Q to X bar of the test configuration. And then the non-Archimedean norm of the test configuration will be computed using the following intersection number as well. Okay, so this is called a norm because if this quantity is 0, then the test configuration is going to be trivial, meaning that the test configuration is a product x cross p1, and the GM action on the fiber is also a trivial action. Okay, so as I mentioned earlier, this non-Archimedean norm is just one of the several equivalent norms of test configurations. And we will need this norm to define uniform K-stability of a Q-Fano variety. Okay, so then I think we are in a good place to define equivariant K-stability. Okay, so X is called K-semi-stable if the generalized Futaki invariant is non-negative for any G-equivariant test configuration. Okay, and if we look at all test configurations, then X is called K-semi-stable. This is the usual K-semi-stability notion. And X is called G-equivariantly K-polystable if first of all it's G-equivariantly K-semi-stable, meaning that the generalized Futaki invariant is non-negative for any G-equivariant test configuration, and the Futaki invariant is 0 if and only if the test configuration is a product. So it doesn't have to be a trivial one. So the action, the GM action still can be non-trivial, but the test configuration itself as a space is a product. And thirdly, X is called uniformly G-equivariantly K-stable if there exists a delta between 0 and 1, such that the Futaki over the norm has a uniform lower bound to be delta for any G-equivariant test configuration. Okay, so these are the three equivariant K-stability notion that I want to mention in my talk. Okay, and here's the note that if we take the group action G to be the identity group, then we will recover the usual notion of K-stability. Okay, so, all right, so before I move on, any question about the definitions? All right, now let's try to look at a couple of maybe very basic examples. The first one is, of course, the projective space. And first of all, for the projective space, we know it's Kähler-Einstein. The Fubini-Studi metric on the projective space is a Kähler-Einstein metric. So according to the solution to the YTD conjecture, so the projective space is K-polystable. However, it is definitely not uniformly K-stable because the automorphism group of Pn is PGLN, and it contains a lot of C-star action. So if a Q-Fano variety is uniformly K-stable, then the automorphism group has to be discrete. So therefore, we know that the projective space is definitely not uniformly K-stable. However, if we consider equivariant K-stability, so if we consider the group action to be the whole automorphism group of the projective space, which is PGLN plus 1, okay, then the projective space is uniformly G-equivariantly K-stable. Because if we try to look at G-equivariant test configuration of Pn, there is actually no non-trivial G-equivariant test configuration. So if a test configuration, if we put an additional assumption, if we want this test configuration of Pn to be G-equivariant, then it has to be the trivial one, meaning that the test configuration itself has to be a product, and the GM action on the test configuration is trivial on the fiber. Okay, so therefore, by definition, it's automatically uniformly G-equivariantly K-stable. Okay, and of course, this means that if you recall the equivariant K-stability conjecture we mentioned earlier, it only deals with the case where about K-semi-stability and K-polystability, and this is the most basic example where actually it fails for an arbitrary group action if for uniform K-stability. So although Pn is uniformly G-equivariantly K-stable, but it's not uniformly K-stable. But of course, Pn is uniformly G-equivariantly K-stable implies that Pn is G-equivariantly K-polystable. And using the equivariant K-stability conjecture, we can deduce also that Pn is K-polystable. This is another way to get that Pn is K-polystable as well. Okay, so this is the very first example. And the same is also true if we look at homogeneous spaces. In that case, for a similar reason, we also don't have a non-trivial G-equivariant test configurations if we take the G action to be the whole automorphism group. All right, so next let's look at another example. And before we look at the example, I want to mention very briefly about Tian's criterion, which is a characterization of K-stability using alpha invariant. So first of all, for a Q-Fano variety with a group action G, we can define the G equivariant alpha invariant of X to be the infimum of all the log canonical threshold of X comma 1 over M sigma, where this sigma is a G invariant linear subsystem inside the linear system negative MKX. Okay, so here we're taking all the G invariant linear systems, and if you recall the usual definition for the alpha invariant, we just look at the log canonical threshold of divisors in the linear system negative MKX, and where we look at the log canonical threshold of the pair X when cover 1 over M X comma 1 over M D, where D is a divisor in the linear system. Okay, so the reason that we want to look at all of the linear subsystems when we look at equivariant alpha invariant is that if G is not finite, it's possible that we don't have enough G invariant divisors, and in a lot of cases we actually don't have G invariant divisors, so we in fact need to look at all G invariant linear subsystems. But if the group action G is finite, of course we can always construct a G invariant divisor by taking the average of the orbit of a divisor. So therefore we can always get a G invariant divisor, and we will see that if G is finite, then it's the same as just look at divisors instead of linear subsystems in the definition of equivariant alpha invariance. So therefore, again, if we take the G group action G to be the identity group, then we will cover the definition of the usual alpha invariant. Of course, this is the algebraic definition of alpha invariant. This is not the definition that is used in Tian's original paper, where he's defining everything analytically. Okay, so there's this theorem of Odaka and Fano generalizing the original results of Tian's criterion, which is purely analytic and for the smooth case in Tian's original paper in the 80s. And so if the equivariant alpha invariant of a Q-Fano variety is greater than or equal to n over n plus 1, or respectively greater than n over n plus 1, then X is going to be G-equivariantly K-semi-stable or uniformly G-equivariantly K-stable. Okay, so of course this is not a if and only if statement. So alpha invariant to be greater than or equal to n over n plus 1 is just a sufficient condition. Okay, and of course in Tian's original paper, he also has a version of equivariant criterion using alpha invariant, which is just for the smooth case. So if we assume the equivariant alpha invariant to be greater than or equal to n over n plus 1, we can actually deduce that X is K-semi-stable. And if alpha G is greater than n over n plus 1, X is going to be X is actually going to be K-polystable, or in Tian's original paper, it's described analytically saying that X is Kähler-Einstein. Okay,
Can
and
I ask a question about this?
okay.
Do you need to make an assumption on the group being compact or finite here, or reductive is enough?
I think I think for the statement here for the Odaka-Sano, if the conclusion is just for G-equivariant K-stability, and I think we don't really need to have any assumption on the group G. So it doesn't even, I don't think it has to be reductive even, just any group action. I think it's okay. However, if we want to get a stronger version, so using equivariant alpha invariant to deduce the usual case stability. So if we want, which is already dealt with in Tian's original paper, then I think we need to assume, in Tian's original paper, I think he assumes that the group G is compact.
I think so, yeah.
And but however, right now I think the statement is true as long as we assume G is for K semi-stability. I think again there's no assumption on G. And however, if we want to get the result of X to be in K polystable, then we definitely need to assume G to be reductive. As long as G is reductive, and alpha G is greater than n over n plus 1, then X is K polystable. Okay. And this is, in fact, an immediate result of the equivariant K-stability conjecture. So we first use Odaka-Sano's result to get X is G equivariant K stable, which of course implies that it's G equivalently K polystable. And then using the conjecture, it's saying that X is K polystable. Okay, so this is the Tian's criteria. Okay, next I want to talk about the example I mentioned earlier, which is the example considered in Chalsov and Shramov's paper about a class of Fano threefolds of degree 22, and among them, they're studying those Fano threefolds admitting the G action, where the G action is a C star semi-product with Z mod 2 action. And they computed in their paper the G equivariant alpha invariance of all these Fano threefolds. And the conclusion is that all but two of them are all but two of them have the alpha invariant to be the equivariant alpha invariant to be 4 over 5. So it's greater than 3 over 4. Therefore, according to the equivariant Tian's criterion, we get that these varieties are uniformly G equivariantly K-stable, and therefore they're K-stable, K-polystable using the equivariant K-stability conjecture. Okay, so this is an example that is, in fact, easier to verify equivariant K-stability to start with, and then we will get the K-polystability of these varieties. And in fact, I think if we try to compute the usual alpha invariance of these varieties, I think they also mentioned in their paper, I think most of these alpha invariants don't exceed 1/2. Therefore, the Tian's criterion actually fails in those cases. So it's we're not in the right position to use Tian's criterion for these varieties, for these Fano manifolds. Therefore, however, by considering equivariant alpha invariants, they're much larger. So we can use equivariant Tian's criterion in these cases. Okay, so these are the two examples that I want to mention. So next, I want to talk about the evaluative criteria of K-stability. So before I move on, any other questions? All right, so for the evaluative criterion, we're first of all going to look at all the prime divisors over a Fano variety. So let E be a prime divisor over X. And so it's given by the following data. We have a proper biisomorphism from Y to X, and E is a prime divisor on Y. Okay, and this E will induce a divisorial valuation on X. And we will denote, first of all, we will look at the log discrepancy of E. which is going to be the coefficient of E inside the relative log canonical divisor ky over x plus 1. Okay, so we will denote the log discrepancy by a sub x of E. And we also have this invariant S of E, which is the expected vanishing order of sections inside negative kx along E. And it's computed using the following integral. And the upper limit of the integral is tau of E, which is the pseudo-effective threshold. So for a large enough x, the volume here is going to be 0. And tau of E is the pseudo-effective threshold, which is the supremums of this number t such that the volume is positive. Okay, so this is the definition of the invariant S of E for any prime divisor E over X. And so the following two invariants are the two invariants that we want to look at in the valuative criterion, which is developed by Fujita and Kento Fujita and Chile separately. So first of all, we have the beta invariant, which is equal to A minus S. A is the log discrepancy and S is the expected vanishing order. Okay, and we have also the J invariant, which is defined as the pseudo-effective threshold, tau of E minus the S of E. Okay, and the statement of the evaluative criterion is the following. So a Fano variety of X is K-semi-stable if and only if the beta invariant is non-negative for any prime divisor over X. And X is uniformly K-stable if and only if there exists a delta between 0 and 1 such that the ratio of beta over J has a uniform lower bound delta for every prime divisor E over X. Okay, so these are the two evaluative criteria for K-semi-stability and for uniform K-stability separately. Okay, so this is the evaluative criterion for the usual K-stability. And next, I want to try to move this whole machinery to the equivariant case. So before I am able to define evaluative criteria for equivariant K-stability, I need to talk about the notion of pseudo-valuations. Okay, so let's start with a group action on a variety X. And if I take any valuation V on X, I can define what we will call a G pseudo-valuation. So we will denote it by G dot V. It's the infimum of small g dot v here, and all small g dot v's are valuations defined in the following way. So g dot v of rational function f is defined to be the valuation v on the function f composed with g. So therefore, defining this way, we can have this small, we can have the g action on all evaluations on x. And if I take the infimum among all these valuations after the g action on the valuation v, this is what we are going to call the g pseudo valuation associated to the valuation we start with. And also, one thing I want to note here is that I call it pseudo valuations because they are in fact not valuations. They don't satisfy the product rule for valuations. And for usually we only have that g dot v of a product is only greater than or equal to the sum of g dot v of the corresponding rational functions. So we don't necessarily have product rule. Okay, and I also want to again look at the associated ideal sheaves of the G pseudo valuations. So first of all, for any valuation, we can have the associated ideal sheaf of regular functions of vanishing order at least x, with respect to the valuation small g dot v. If I take the intersection of all these ideal sheaves, then I have this ideal sheaf associated to the G pseudo valuation, capital G dot V. Okay, so this is the ideal sheaf of regular functions of vanishing order at least x with respect to all these valuations small g dot b. Okay, and I think there's a question in the discussion. Yes. So I think in the Fano and Mustasa's paper, they define the notion of pseudovaluations in more general for any on an affine variety. So here this definition falls into that that category. So this is and they are in fact pseudovaluations in the sense of Tommaso de Fano and Mustasa. Okay, so I think this is all I want to talk about about pseudovaluations. Any other questions before I move on to talk about the equivariant valuative criteria? Okay, so now I think I'm in a good place to define equivariant version of all those invariants for the usual valuative criterion. So first of all, for a divisor over x, again, we want to define the equivariant version of the S invariant. So this is it's defined again using similar integrals. However, here we are looking at the volume of sections of vanishing order at least x along all the valuations in the orbit of the G action on the divisorial valuation defined by E. So let me go back to the previous slides of the usual valuative criteria. So for the usual S invariant, here we're looking at the volume of sections of negative kx of vanishing order at least x along E. However, for the equivariant version, we look at sections of negative kx. Here we're looking at the ideal sheaf. So this ideal sheaf as defined in the previous page here, it actually collects sections of vanishing order of at least x along all these valuations G dot or E. Okay, so this is the definition of the equivariant S invariant. And of course, again, the upper limit of the integral, we have the equivariant pseudo-effective threshold. So this is the supremum of the number t where the volume is positive. Okay, and then again, we can define the equivariant invariance that is used in the equivariant valuative criterion. We have the equivariant beta. So the log-canonical threshold, the log discrepancy of the divisor E is the same one as we used in the usual valuative criterion. And so in the definition of equivariant beta, we use equivariant S invariant. So equivariant beta equal to A minus equivariant S. And we also have this equivariant J to be equivariant tau minus equivariant S. Okay, so this is parallel, basically everything is parallel to the usual valuative criterion. Okay, and then maybe I also want to note here, so if we are looking at invariant divisors over X, then this is just the same notion as the usual ones in the usual valuative criterion. So when we look at the G pseudo valuation G dot or E, this is going to be the same for any small g. So this is again just the divisorial valuation defined by E. So then everything is just the usual one. Okay, and so next I want to talk about the equivariant valuative criterion. So instead of looking at all prime divisors over X, in fact, I'm just going to look at divisors, prime divisors of finite orbit over X. And the definition of a prime divisor to be finite orbit is that the orbit of the valuation under the G action is finite. Okay, so first of all, recall that if I have a group action on the variety X, then the group action also acts on all valuations on X. So for a prime divisor, we can have a G action on the corresponding divisorial valuation, or E. And then I can look at the orbit under the G action. And if the G orbit of this action is finite, then we say that this prime divisor E, or the corresponding divisorial valuation, is a finite orbit. Okay, so, and I want to also mention here that if we are looking at the group G to be, if we are looking at a connected group G, then a prime divisor being finite orbit is the same as saying that this divisor is G invariant, because the orbit of the if we start with a connected group, then the orbit of a divisor is also supposed to be connected, and therefore, if we are looking at a prime divisor of finite orbit, then it has to be G invariant. Okay, and so now let's go through the statement of the equivariant valuative criterion. So a Fano variety X is G equivariantly K-semi-stable if and only if the equivariant beta is non-negative for every finite orbit prime divisor E. And also for if a Fano variety X is uniformly G equivariantly K-stable if and only if there exists a delta between 0 and 1 such that the equivariant beta over the equivariant J has a uniform lower bound delta for any finite orbit prime divisor E. And as I mentioned earlier, if G is connected, then this is all these statements are concerning G invariant divisors. And we also mentioned earlier that these equivariant notion coincides with the usual notion. So for G equivariant K-stability, when G is a connected group action, then we only need to change the statement in the usual valuative criterion to G invariant divisors. Okay, and for a finite group action, of course, all prime divisors are a finite orbit. So therefore, we are actually looking at all prime divisors over X in the statements for G equivariant K-stability if we look at finite group action. Okay, so this is the equivariant valuative criterion. And so next, I want to mention an application of the equivariant valuative criterion. And so the application is for a finite group action. So actually also from now on in my talk, I'm going to assume the group action is going to be finite. Okay, so if we start with the finite group action, we can actually look at the quotient map. So we have the quotient map sigma from X to Y, where Y is X mod G, which is a finite, sigma is a finite map under the finite group action. Okay, and then we have the following relation of the canonical divisors, which is a higher dimensional generalization of the Hurwitz formula. So Kx is the pullback of Ky plus the sum of all the ramification divisors, where the coefficients are the ramification index minus 1. Okay, then we want to consider a boundary divisor B on the variety Y downstairs so that we can write Kx as the pullback of Ky plus B. So the B is constructed in the following way. It's the sum of 1 minus 1 over EI times BI, where BIs are the branch divisors. And so if BI is the image of the ramification divisor R, and the ramification index of R is EI, and So for all the ramification divisors over BI, they are going to be the same because we're taking the finite group quotient here. So therefore, we have the same ramification index for all the ramification divisors R, and therefore we will denote this ramification index corresponding to BI as EI, and then we construct this divisor B as the sum. Therefore, using the formula above, we see that we can write Kx as the pullback of Ky plus B. Okay, therefore, starting from variety X, we construct a pair Y comma B downstairs so that the pullback of the log canonical divisor is the canonical divisor upstairs. All right. Okay, so next I want to talk about I want to talk about a result relating K-stability of a Q-Fano variety with this quotient under a finite group action. Okay, so first of all, following the notation previously in here, so if I start with the Q-Fano variety X, then negative Kx is ample. Therefore, we know that the pair downstairs Y comma B is going to be log Fano because Ky plus B, negative Ky minus B is also ample. And also, I didn't mention it earlier, but all the previous results actually works for log Fano pairs. So in the statements of the previous results and in the proof, if we replace the canonical divisors of the Q-Fano variety with the log canonical divisor of the log Fano pair, then everything works identically. So therefore, all the results will work for log Fano pairs. So I'm not going to repeat corresponding statements. So then we have the following result. So using the notation here, we have that if X is G equivariantly K semi-stable, then the pair downstairs is also K semi-stable. And if X is G equivariantly, uniformly G equivariantly K stable, and then the pair downstairs is also is going to be uniformly K stable. And the converse statement is also true. Okay, so basically this is a proposition relating the K-stability, equivariant K-stability upstairs and with the usual K-stability of the log Fano pair downstairs. All right, and let me mention very briefly the idea of the proof. So for the only if part, if we assume G equivariant K semi-stability of X upstairs, then we can look at the beta invariant of all the divisors over the pair Y comma B downstairs, and then we can pull back the prime divisor E to we will get a corresponding prime divisor X, prime divisor over X upstairs, and then we can compare the corresponding beta invariants. So we have equivariant beta invariants upstairs and equivariant beta and the usual beta invariant downstairs. And if we compare the beta invariants, we have the right direction of the inequality of beta invariants, which will give us the only if part, so of K semi-stability. And for uniform K stability, the idea is very similar, except that we also want to deduce the same direction of inequality for the J invariant, or more generally the norm of the norm determined by the J invariant. Okay, so this is the only if part. And for the if part, so if we know K semi-stability of the pair downstairs, then we try to look at all special test configurations upstairs. And then we can take the quotient under the G finite group action, G, to get test configurations downstairs. And then we can compare the Futaki invariant, because the Futaki invariant can be computed by intersection numbers. And then we can relate the intersection numbers by the pullback. So the sign doesn't change, and we also get the corresponding results we want. Okay, so therefore for the if part, we are looking at Futaki invariance of test configurations, whereas for the only if part, we look at beta invariance of X, and both of them characterize as K-stability. Okay, so this is a very brief sketch of the proof for the proposition. Okay, so next I think I want to mention the, so lastly I want to mention the main results in my joint work with Yuchen, so which is the proof of the equivariant K-stability conjecture for the finite group action. So if we assume X is X is a Q-Fano variety under a finite group action, then X is G equivariantly K-semi-stable, implies that X is K-semi-stable. And if additionally we assume it's G equivariantly K-polystable, then it's also K-polystable. Okay, so let me first of all mention the sketch of the proof for the K-semi-stable case. Okay, so the first step is the proposition I mentioned earlier. So if we assume X is G equivariantly K-semi-stable, then we look at the pair resulting from the quotient, then the pair Y comma B is going to be K-semi-stable from the proposition. Okay, and then we want to use the perturbation result from Bloom and Liu, where in the paper they studied the semi-continuity of delta invariance. We have this perturbation results saying that if I perturb the boundary a little bit by epsilon, where the divisor d prime in the Q-linear system of negative ky plus b, then we can get a uniformly K-stable pair, y comma b plus epsilon d prime. Okay, so starting from a K-semi-stable log-Fano pair, if we perturb the boundary a little bit, we can get a uniformly K-stable log-Fano pair. Okay, so the next step is where we need to use the analytic result, which is the uniform YTD conjecture. So if the statement of this uniform YTD conjecture is that if a log-Fano pair is uniformly K-stable, then we have the existence of a Kähler-Einstein metric on this log-Fano pair. Okay, so this is proved recently by Li Tian Wang using analytic method. So this is a generalization of the usual YTD conjecture for the smooth case, which is solved by the well-known results of Chen, Donaldson, Sun, and Tian. Okay, so therefore we know this log-Fano pair is Kähler-Einstein. Okay, so the advantage of having the existence of Kähler-Einstein metric is that it is easy to pull back this Kähler-Einstein metric. Although it's in fact not very easy to pull back K-stability conditions, but pulling back Kähler-Einstein metric is relatively easy. So therefore, if we pull back this Kähler-Einstein metric upstairs, we have this pair x comma epsilon d to be Kähler-Einstein. So we pull back this metric, it's also Kähler-Einstein upstairs. And here d is the pullback of d prime downstairs. So d is a divisor in the Q-linear system of negative kx. All right, so then we have this Berman's results. So the existence of Kähler-Einstein metric implies that this log-Fano pair is K-semi-stable. So this is the Berman's result, which is one direction of the YTD conjecture for the singular case. So the existence of Kähler-Einstein metric implies that this pair is in fact K-polystable using Berman's results, and then in particular it's K-semi-stable. Okay, then again, using Bloom-Lewis perturbation result, we can take this epsilon to go to 0, and we have that X is in fact K-semi-stable. Okay, so this is a very brief proof of the K-semi-stable case of the equivariant K-stability conjecture. Okay, so a very important part inside the proof, in fact, is the uniform YTT conjecture, which is purely analytic. Okay, so so I would say that maybe this result is in fact an analytic result. So all the other part of the algebraic part of the proof is mostly quite straightforward. Okay, so next I want to talk very briefly maybe about the K-polystable case. So I maybe have a couple of minutes. But before I move on to the K-polystable case, any question about the result, also the proof of the K-semi-stable case? Okay, so for the K-polystable case, I will use some of the language we use for the construction of the K-moduli of Q-Fano varieties. Okay, so in order to show that X is K-polystable, we want to prove by contradiction. So if we assume X is strictly K-semi-stable, then by a result of Li Tian Wang, we will have a special test configuration of X degenerating X to a K-polystable X naught. Okay, now we want to use the language of K-moduli. So the existence of such a special test configuration corresponds to, first of all, an entire neighborhood of X naught, which is the K-polystable point in the K-moduli. And also we have an entire neighborhood of this K-polystable point of this foreign spec A mod H, where H is the automorphism group of X naught. And X corresponds to some other points inside spec A. So this automorphism group of X is a subgroup of H, which is the automorphism group of X naught. And G is a group action on X, so it's also a subgroup of H. Okay, and a test configuration of X, basically we can interpret it in the language of K-moduli as a morphism of A1 mod GM to the K-moduli, or here I'm looking at an entire neighborhood of this K-moduli. And this morphism sends 1 to the point X and sends 0 to the special fiber X naught. And also equivalently, this is the same as giving a one parameter subgroup GM as a one parameter subgroup of H. Okay, and also the limit of this one parameter subgroup when t goes to 0 degenerates X to X naught. Okay, so this is the setting if we start with the special test configuration of X degenerating X to X naught. Okay, so we want to deduce the contradiction by using the original data to get actually a G-equivariant test configuration. Then we will get a contradiction. So our goal therefore is to find a G-equivariant data, which is a phi prime, so that is equivariant, G-equivariant. So a priori, for arbitrary test configuration, it doesn't have to be G-equivariant. Okay, so this is the existence of a G-equivariant test configuration is guaranteed by a result of Luna about the closeness of orbits. So starting from lambda, a one parameter subgroup from GM to H, degenerating X to X naught. In fact, we can get a one parameter subgroup lambda prime, which is a one parameter subgroup of the centralizer of G inside H. And it still degenerates X to X naught when t goes to 0. So this is guaranteed by the closeness of orbits by a result of Luna. And the good thing about a one parameter subgroup of the centralizer is that it actually commutes with G. Okay, therefore, this one parameter subgroup will give us a G equivariant test configuration. And this G equivariant test configuration degenerates X to X naught. Therefore, the Futaki invariant of this test configuration is 0, and it's definitely not a product test configuration because the central fiber is X naught, which is not X. Therefore, it's contradicting to the assumption that we assume X is G equivariantly K-polystable. Okay, so therefore, the assumption that X is strictly K-semi-stable is false to start with. So therefore, we know X is K-polystable. Okay, so this is a very brief proof of the K-polystable case. Okay, so I think time is up, and I'll probably stop here. So thank you very much for listening.
Thank you very much. It was a very enjoyable talk. I just want to make a comment. I think the quotient proposition relating K-stability above and below a finite group action, I think maybe part of it or most of it was first proved by Rui Dervan.
Oh yeah. Oh yeah. Maybe that's definitely, I should definitely mention that result of Dervan. So I think if I recall it correctly, I think for in Dervan's results, mostly it's about the case when G is cyclic, if I remember it correctly. Okay. Although I think, of course, in Dervan's original paper, he's mostly focusing on smooth case, but I think his method probably generalizes to singular case as well. But if I remember correctly, in his paper, all statements is in terms of G to be cyclic.
Okay. Okay. Do we have any more questions or comments? Okay, I'll make a question then. So this conjecture is still open if the group is arbitrary then?
I think if the group is arbitrary, it's not going to be true for.
Okay,
yeah,
reductive.
It has to be reductive. Yeah. So if G is reductive, I think it's already solved in Ziwen Zhu's paper. Okay. So I think right now for this conjecture, all the cases are solved in Zhu's paper.
Okay, cool.
Yeah.
So it's not a conjecture anymore.
Yeah, it's not a conjecture anymore. It's true right now.
Okay, thank you very much. Thank you, everyone. See you next week.